Okay. Okay, should be working. Um, okay, so today we have the pleasure to have Professor Renaud Lambiotte, who will talk about consensus and random walks on higher order networks. Our speaker is a professor of networks and nonlinear systems at the Mathematical Institute of the University of Oxford and a tutorial fellow at Somerville College. He's also a Turing Fellow at the Alan Turing Institute in London and an external faculty member at the Complexity Science Hub in Vienna. Um, he is author of more than 100 peer-reviewed publications and three books, which are, if I'm not wrong, A Guide to Temporal Networks, published by World Scientific in 2016, Complex Networks and Their Applications, published by Springer in 2019. And last but not least, Modularity and Dynamics on Complex Networks, Cambridge University Press 2021. And if I am not wrong, he has also created a book collection on the relation between science and literature, entitled La Tortue de Zenon, for which he was awarded with the Verdict Rijdams. I'm not sure about the pronunciations. I'm sorry, actually.
You did your
Prize
best.
by the Royal Academy of French Language and Literature in 2016. So, well, that said, I thank you again for being here today, and the floor is yours.
Okay, well, thank you very much, and thank you for looking so carefully into my CV. So, well, just a small, well, a tiny correction. So, the second book you mentioned was just the editor, so it's not really a proper book. I just wrote the preface, and I helped to select like the people who would be like participating to the chapters. But thanks a lot, and actually,
Yes.
indeed, in order to talk about this collection of between science and literature. So, for those of you speaking French. If you like science and literature, we have a whole collection of books. I'm happy to send you the PDF of the books if you're interested in, or you can send me a message if you want to hear about it. But in any case, today I'm going to be talking about something quite different. So what I'm going to be talking about is is a collection of works that are somehow all related to the notions of consensus dynamics, diffusion, and usually diffusion in my case is going to be modeled as some sort of like a random walk process. When you define these dynamical process on structures that are somehow generalizing the notion of graphs. Now, so this talk really finds its inspiration in a perspective paper that I wrote with Martin Roswell and Ingo Scholz already 6 years ago, and where I think that the first ideas came from that perspective paper and then it's been built on over the last few years. You can feel free to interrupt me at any point if something is not clear. I'm happy to provide you with some questions if it's needed. Just before I continue, Cosimo, am I right that the talk is for like 50 minutes or so, something like that?
Yes, exactly. It will be around 50 minutes and then questions and answers.
Okay, wonderful. And feel well, don't hesitate to interrupt me if I'm too long.
Okay, thank
Okay,
you.
perfect. Thanks. Great. So let me start. We actually it's a slide that I use for the course that I have a course on networks that I give at the University of Oxford, and it's a slide that I use because I want to emphasize to the students that well, networks are obviously not reality, right? Networks are an abstraction of reality, a way for us to take some real data, to take some observations that we have, and to translate them into a language that we can use to understand it. And here is an example where to show you the power of networks, where on the left-hand side you have a map, and that's a map of of Königsberg, where you have the bridges, the famous bridges. And when you go from the left to the right, you are getting rid of details because the modeling requires you to get rid of unnecessary aspects of the data. And if you get rid of the physical locations of the different parts of the cities, if you get rid of where the buildings are placed, what you get when you go to the right is a graph representation of the city. When you do so, clearly you are throwing away certain details of the city, but what you emphasize, what you keep is the essence of connectivity. What you keep here is a graph representation, and this graph representation is all that you need if you want to understand how people can walk around the city by taking the bridges. And that's all that you need if you want to find a solution to the famous problem of the Königsberg bridges. Now, it means here that when you go from the left to the right, where you've been throwing away certain information, and what you gain is a very general and powerful language, the language of networks, that can be used in order to represent not only cities, but a variety of systems. Now, the graph theory is a fairly old field, but it's a little bit more recently, and I think arguably it dates of the last 25, 30 years, that people have been interested in the combination of graphs, networks, and dynamical systems. And actually, when I moved to the field of what people will call now network science, well, there was a very beautiful review paper that was written by Mark Newman. It was published in the Science Review on the structure and function of complex systems, where basically he was emphasizing that, well, the function of a system is associated to its dynamics. And the essence of what we call now network science is really understanding how the structure and the dynamics of a system are related with each other. Now, very often when you consider dynamical systems on graphs, what as a first step, what you would be doing is to look at some linear dynamical system. And I will give you a few examples after, and especially in relation to diffusion. But very often, if you look at these linear dynamical systems, the kind of equation that you're going to be having to solve would be an equation like the one that you have here, where x is a vector that encodes the states on each of the nodes. And what you have is that the time evolution of that vector, of the states on each of the nodes, is determined by what you have here is a matrix times that vector. And that matrix is basically a matrix that encodes the connectivity and how the connectivity affects the changes. And very often, well, you will have that this matrix L is going to be somehow related to the adjacency matrix of the graph. It could be the Laplacian, it could be the transition matrix. But in most of the interesting cases, it's going to be a matrix where the non-zero entries are the same as in the case of the adjacency matrix. It basically means that when you do L times X, what you're doing is basically looking at all of the values of X for a certain line, for a certain node I. When you look at the corresponding entry of L times X, what you're doing is a linear combination of the states of the neighbor of that node I. And depending on the values of the entries, you're going to be having like a certain weighted sum of the values around the node I. But the most important is that you have a linear combination of what's happening around the node. So what's happening at node xi is determined by a linear combination of the states of its neighbors, basically. And this is the core of what you have when you have a linear dynamical system on the graph. Now, the thing is that this type of equation is, well, potentially a large uh, system of linear equations, and that's something that students learn to solve in their first year or second year of university. Specifically, when the matrix L is symmetric, you can just diagonalize that matrix and you will find, and you can find formally that X is going to be obtained by taking the exponential of the matrix L. But that's not the end of the story, because as I will explain in just a few moments. So before I talk about that, about how to solve that equation and how it relates to graphs, let me take a step back for a few seconds. As I said, this kind of approach where people started to be looking at how networks and dynamics were related with each other, it really dates back, at least for me, at the wonderful work of Watts and Strogatz of 1998, which is really a wonderful paper. For those of you who didn't read it, I know it's an old one for your generation, but honestly, it's a wonderful one, even as of today. And what was actually quite marvelous about that paper is that it took the problem of collective dynamics and put networks into it. And if you go to papers that would be before that seminal paper, when people looked at collective dynamics, they would either look at collective dynamics in a mean field case, where you would have like a certain number of agents that are all interacting with each other in a random fashion. Or they might be looking at what would be happening on a very regular lattice, inspired by physical problems, where you would have a one or two dimensional lattice. But actually, what was quite beautiful about the work of Watts-Stroger is that they started to question these two extremes, and they considered what would be the dynamics on a graph that would be more arbitrary. Now, and one of the first consequences that they observed is that the graph matters, right? So the graph has a strong impact on the way the dynamics takes place on a system. Now, something that is very beautiful about graphs, and that is quite important to keep in mind, is the fact that graphs are not just a collection of nodes and edges. If you just think of a graph as like m edges that are connecting pairs of nodes, well, that's not bad, but it's relatively underwhelming, if I may say. What is really beautiful about the graphs, the graph structure, is that there is a possibility to combine incident edges in order to form indirect paths inside a system. And what is beautiful about networks is the fact that they allow you to combine sparsity and connectivity together. Most of the graphs that people are interested in are sparse graphs. They have a very tiny density of edges as compared to the maximum density that would be possible and would be on the order of n square. And very often the number of edges is much, much smaller than n square. But yet, despite the fact that they are sparse, they allow for connectivity because of the possibility for signals to propagate indirectly, taking a sequence of edges inside the system. So it means that graphs are powerful because they are sparse and connected. They allow for connectivity through indirect connections. Now, if you go back to this equation that I gave you before here, right? So as I said, students in first or second year could solve it formally. But actually, what makes the problem interesting is to try to understand how the matrix L. And if you want to solve this system of equations, well, it's going to be solved if you know the eigenvalues and eigenvectors of that matrix L. Well, the problem starts to be interesting when you try to understand how these spectral properties of that matrix are related to some graph properties. And typically, people would be looking at this problem from two sides of the same coin, from two complementary perspectives. On the one hand, they would try to understand how certain aspects of the graph structure are impacting the dynamics. So, for instance, is the degree distribution or is the density of triangles or does modularity structure affect the eigenvalues and eigenvectors and hence influence the dynamical process? And that could be in terms of acceleration or slowing down, for instance. So you try to understand how certain graph structures are impacting the spectral properties of that matrix L that you have. But similarly, people also try to use this system of equation that you have here in order to simulate diffusing dynamics on graphs in order to uncover important information that would be hidden in those graphs. And that actually is a strategy that is extremely powerful for many reasons. In particular, because when we will be looking at random walks, well, you can write random walk dynamics with this equation, but you can also simulate it by Monte Carlo simulations, and you can do these simulations across multiple computers. So it's very easy to distribute like a random walk process across computers. And if you look at the trajectories of random walks, so if you try to solve equations like these that simulate random walk processes, well, you can use that as a way to explore the graph less locally than just looking at the matrix L. And this is an approach that is at the core of a lot of works for instance, network embeddings. So you try to embed nodes in some low-dimensional space, Euclidean space usually. Or you can also use that for centralities. So the very famous PageRank is associated to a random walk process and as the stationary state of that process. And this is a very popular way, even as of today, to rank the importance of nodes in directed networks. Or also, and I'll come back to that point a little bit later, for community detection. So several approaches for community detection, at one point or the other, are somehow using IDs or intuitions that come from random walk processes. And so here, well, what is the take-home message of this slide here is the fact that, well, this equation is in principle easy to solve, but it's interesting and it still is an active research question when you want to understand how the matrix and the graph are related with each other. Now, and here is just like a tiny example to show you this connection that exists between the dynamics and the graph structure. And that's actually like a picture that is taken from the book that was mentioned by Cosimo. So I don't do that so that you buy the book. As you'll see at the very end of the talk, if you stay until the end, I will give you the link where you can download the PDF of it. So just be patient or come back in 45 minutes and you can get the full book for free. And here what you have is, well, the famous Karate Club. And where you have like these relatively well-defined communities that are here painted in red and blue. And here what I'm just showing is what would be happening if you were to start a random walk process either on this red node here or on that blue node there. That are the two high degree nodes of each of the two communities. Now, a random walk on a graph is defined by typically the simplest one is in discrete times at each step a random walker is on a node, looks around and if there are 5 nodes with it tries to it takes one edge with a probability of 1/5 in a random way basically, and then at each step it takes an edge randomly, independently of the previous choices. Now, if you look at a random process of an undirected network, it's known that if the graph is not bipartite, if the graph is connected, which is the case here, asymptotically, you converge to a stationary state and the graph and the dynamics is ergodic. So independently on your initial conditions, you reach the same stationary state. And in the case of undirected networks, what can even be shown is that that stationary state is such that the density of walkers or the probability to find walker on certain node is proportional to the degree of that node. And this would be this distribution you have on the right, where you indeed have that, for instance, if you look at node 12, I don't know where it is, it's around here, it has a degree of 1, right? And you can see that at stationarity, it has a very small probability to find walkers on it. So that makes sense. And what you can see is that independently on your initial condition, you converge asymptotically to the same stationary state. So the theory is right. Now, what is interesting is the fact that actually, if instead of looking at what's happening in the asymptotic regime, but a little bit before, and by a little bit before can be quantified by looking at the eigenvalues and looking for certain spectral gap between certain eigenvalues, but it's not really so important here. But what is important is that at a certain time, what will happen in the case when the graph is made of sufficiently well-defined modules or communities, you will actually have that if you start from the red node, around those times, what you will observe is something associated to time scale separation and to a certain like quasi-stationary state as it's defined usually, which basically means it's a complicated word just to say that if around those times the walkers that started from the red node have had enough time to explore the red nodes and to reach a distribution that is close to the equilibrium one within the red. And you can see that this one here looks like the one there, right? But it didn't have enough time to explore the blue yet. Yeah. And so you can think of this process as until that time, the walker starting from the red node explore the red, and only later on does it explore the blue and reaches the asymptotic state. If instead you start from the blue, what happens is that for these intermediate times, you reach a distribution that looks like the stationary one within the blue, but the red have not been explored, and it's only at later stages that you reach the full stationary state. So actually, this picture is quite important because, well, it really makes a connection between certain graph structures, and in this case, that would be the presence of communities, and something called time scale separation, the existence of different scales. Here, there would be a fast scale at which nodes converge to this local equilibrium in a way, and then a slow scale so that asymptotically you reach the full equilibrium here. And the thing is that this information is actually something that people can use in order to build metrics and to build like methods to uncover information from graphs. So for instance, if you use the values that you have here, you can use those values in order to define some similarity measure between nodes that will basically tell you that the red nodes are similar and that the blue nodes are similar, and but that the red and the blue are not similar with each other. And a lot of methods are using this kind of information that is defined at the transient times in order to infer indirect relations between pairs of nodes. Now, so as I said, random walks are great because first of all, they allow you to go from the local to the global. You can explore if you just give one step to the walkers, they take one edge. But if you give more than one step, they can go and explore further away. So they have this possibility to interpolate between local and global properties. Second of all, they have like extremely solid theoretical background or like properties because, well, they can like the dynamics of random walks can be written in terms of matrices, so you can use linear algebra. But also there is like a well-developed branch of math called Markov chains that are essentially equivalent to the theory of random walks on networks. So everything that from Markov chains can be used in order to understand dynamical like random walk processes defined on graphs. As I said, that they are easily deployable in a distributed setting because when you look at let's say 1 million random walkers, each of them is independent. Each of them are moving independently of the others. And so they can be distributed across different processes. And as I said as well, these random walks are used in a variety of settings and algorithms for networks that would include community detection. And for that, there is, for instance, Markov stability or the map equation. That is a wonderful technique that is also based on random walks. Centrality, like PageRank, but also similarity measures, such as the effective resistance. That can be, so the effective resistance is something that comes from electric circuits, but can be formulated in terms of the mean return times of random walkers. So the time it takes for a walker to go from A to B back to A, and it can be shown to be a proper metric of like a distance, like a metric distance between pairs of nodes in networks. But also something called node to vec that I will explain in a few moments. That is also a very efficient and very popular technique, more used in computer science, in order to find similarities between pairs of nodes in networks. Now, so random walks are great because they are extremely well easy to understand. They have great properties. But there's just something that needs to be kept in mind is the fact that very often there is more than one way to define a random walk process on a graph. And so it means that if you have a graph, well, even if the graph is undirected and if the graph is undirected, there are more than one way to define a random walk process on the same graph. And for instance, in the case of undirected networks and unweighted networks, the two canonical ways are associated to two matrices, one called the normalized Laplacian, the other one called the combinatorial Laplacian. Both are actually exactly the same if you define them on regular networks. Networks where all of the nodes have the same degree. But as soon as the nodes have different degrees, they become different. And because they can be different, it means that the algorithms that are downstream of the definition of the random walks can lead to very different conclusions. Here is, without going into the details, the result of community detection on using exactly the same method, Markov stability, on the same graph, but in one case using the normalized, in the other case using the combinatorial Laplacian. And you can see that the clusters are quite different. And that's something that needs to be kept in mind, and I will emphasize that later, is that sometimes when you need to develop or to use algorithms based on random walks on some data, one needs to think a little bit about what is the right random walk process that needs to be used. What is the one that is the closest to the to the intuition that we have about how processes take place on the empirical data that we aim to model. And actually, this is indeed something that is quite important to keep in mind, but can also be leveraged. And so I talked a little bit before about node to vec. So node to vec is essentially like based on a second order Markov model. So here, what it means, and I will explain higher order Markov models a bit more later, but let's assume that I go from, so I transition from the node V. Well, let's assume I forgot about the letters of that specific example. So let's assume that I go from I to J, right? And then actually in Node2Vec, you have different probabilities depending on whether or not you have a tendency to backtrack, you have a tendency to go back where you came from, or you have a tendency to go to one of well, here that would be I start from xi and I go to v, right? So there would be a certain weight of going back where I came from, a certain weight that favors or not the possibility to go to one of the neighbors of where I came from. And the intuition here is that the resulting random walk is going to be constraining the walker in the same region of the graph, right? I go back not to the same node as before, but to one of the neighbors of where I came from. Or I go to a node that is not connected where I came from, and that would be some sort of like exploration, pushing me away from where I was at the previous step. And so here you have a model where you have two parameters, the P and the Q, that give more or less importance to these triangular steps or to these steps that push you away from where you came from. And actually in Node2Vec, one of the important steps of this algorithm is to learn from data what are the optimal choices of the P and the Q, such as to solve a certain task. And so it means here that they leverage on the possibility to enrich the model, to have like different parameters for the model in order to find what are the best model parameters in order to solve a certain task. And they do it in a more machine learning way by learning that on some data sets. So it means that having some richness, having the possibility to have like a family of workers, well, it's something that sometimes can be exploited in order to improve the accuracy of models, for instance. Now, so far I've only talked about networks. But the thing that over the last, well, for a long time now, it's been recognized that data that we can gather, that we can collect in empirical studies, they tend to be fairly complex and rich, which means that you have the possibility to combine different aspects of the data together. And you can look at a certain data set in a relational way, that would be graphs, but you could also look at it from a temporal perspective, or you can look at it from a more geometric perspective, or even, and I didn't do it here, using some semantic information if you're using some textual data. So it means that the same data set combines usually multiple, like multiple types of data and may require a collection of tools across methodologies. Now, the things that with Martin Roswell and Ingo Scholz, a little bit more than 10 years ago, we started to be interested in this possibility to enrich networks. So to go beyond from a purely relational model to generalized model that would make the model more rich and potentially more accurate in order to represent real life systems. And we started to run these workshops called higher order models in network science. And well, after more than 10 years of those, well, if I try to summarize the kind of talks that we had and the kind of limitations that people recognized in using networks for real life data, there would be that, first of all, in many situations, well, one assumes that the building block that people use in order to define networks would be pairwise edges. Whereas in certain situations, actually, you need building blocks that wouldn't be edges, but more complicated motifs. Another one is that a lot of works are assuming that networks are constant in time, whereas they are highly dynamical entities. Another one that is maybe a bit more difficult to explain now, but hopefully it's going to be more clear later, is the fact that once you have a graph, you have a Markovian idea of dynamics, in the sense that a graph is stored in a matrix, and the matrix doesn't tell you how a certain sequence of edges is taken by some agent. Actually, if you look at empirical data, and if you try to look at the way people, for instance, are navigating a graph, or how certain information is spreading inside the graph, it can be observed that very often it wouldn't be well modeled by a Markovian model, but actually requires some higher order Markov modeling. And here, it basically means that you cannot not simply combine in these incident edges to define path. You need to add additional information requiring higher order information. And then finally, something that actually I've started to be much more interested in recently is the fact that very often there are situations where edges may be equipped by weights. We know weighted networks, but these weights need not be real. They can be real and negative, but they can also be not real, complex values, but they can also be matrices themselves. You can have that each edge could be a matrix that leads to a linear transformation of signals between nodes. And this is actually something that I will try I hope I will have the time to say a few words about these generalizations as well. Now here today, I'm going to be focusing. I don't have much time. Well, I have time, but not enough to do everything, I guess. So I will not look at temporal networks because it's a little bit older. I will focus on the first one because it's the most relevant one for your research network, I think. And then I will also talk a little bit about the last two, if I have the time. And the kind of like idea that are pervasive to what I'm saying here, as I said, were developed in this review paper from Nature Physics. Now, how do you do to generalize networks and graphs? Well, there are different languages that people can use in order to encode, like, to have a language for networked systems, networks of interactions, but where the interactions involve more than two nodes. And here in the following, I will focus on hypergraphs that are a very flexible way to do it. People might be interested in simple shell complexes, but here in this case, I use hypergraphs because I find them a little bit more, let's say, a little bit more flexible as a mathematical modeling framework to encode higher order or like multiple interactions. And the thing is that clearly a hypergraph encodes more information than a graph. Yeah. And in a hypergraph, what you can think of is that you have groups of nodes that are interacting in a cliquish way together, and you have like a combination of multiple cliques, but these cliques cannot be decomposed into edges. The cliques are not decomposable. And you need to deal with this system of cliques and trying to understand how this system of cliques, potentially of multiple sizes, are forming some large scale structures or may lead to some collective dynamics. Now, actually, when there has been, well, first of all, hypergraphs are not a new topic, right? Hypergraphs are very, very old. There are plenty of books on the topic in graph theory. But again, looking at the relation between hypergraph theory and dynamics, in the same way that network science is about the relation between graph theory and dynamics, is actually something that is much more recent. And actually, over the last 10 years or so, there's been like different approaches where people try to adapt concepts from network science within the study of hypergraphs. And so, for instance, there was this nice work of Austin Benson generalizing the notion of cuts, the notion of Cheeger inequality, to the case when you would define the cuts between sets of nodes in terms of how the cliques were basically cutting, we're going from one part of the hypergraph to another part of the hypergraph. But there have been like multiple works on community structures, clustering, centrality, and so on and so forth. Now if you want to look into dynamics now, which is the part that I am the most interested in, well, the first thing would be to look at the possibility to have like an interesting dynamical model, a model that rebuilds on these high order interactions on these cliques. And a question that is very important is, let's assume that I have a certain hypergraph here. Well, this hypergraph can always, and I will be a bit more specific later, can always be represented by a graph. So when you have a hypergraph, you can always find a way to project that graph onto a weighted graph. And there are multiple ways to do it, simple and more complicated ones. But once you have a graph, you can always see that graph as a hypergraph. In this case, it would be that you have an edge here, and this edge has as a weight the number of hyper edges to which it belongs. And here, this one belongs to one single hyper edge, so it has just a weight of one. And here I started from a hypergraph and I have a graph, right? And when you look at dynamics, the first question that you may want to understand is, how is the dynamical system affected by this change of representation from the hypergraph to the graph representation? Do you observe something different if you go from here to there, or do you observe the same dynamics, basically? And well, here, in order to study this problem, this all started 5 years ago with Leonie Neuhauser, So she was a master student in my department. And well, actually, we had to finish this project. I think it was during the times of COVID, if I remember well. But it was a very like a wonderful one of these wonderful collaborations with the students where you work on that for 6 months. She had a great dissertation, and then we decided to finish it and to turn it into a paper. And in this case, what we wanted to do was to look at a simplistic model of consensus dynamics, having nodes that basically are trying to reach a consensus with their neighbors, but where we would be using this higher order information that is encoded, in this case, by triangles. We just looked at hypergraphs with triangles as the next generation to graphs with pairs of nodes. So we go from size 2 to size 3 for the interactions. And the kind of interaction that we had in mind would be some sort of reinforcement where if you would have that two agents are similar, they may be able to be, well, they would be more convincing on a certain node than if the two agents are not basically not having synergies with each other. And the idea was that so the way two nodes impact another depends on the states of those nodes. And how it works is the following. So we decided to go from the pairwise to the three-body interaction. And in the case of the pairwise, in a nonlinear setting, what you have to solve as an equation would be something like that. The way node xi changes is a linear combination of a certain function that depends on the state of node I and the state of its neighbors. So I look at this node, and then you have a linear combination of a nonlinear interaction with this one, that one, and that one. If you go now to the case of three-body interactions, what you need to do instead is to sum over all of the triangles, and the triangles are encoded in this tensor of size 3. And where in this case you would have that I look at how I is impacted by the interaction coming from J and K, and where I is impacted from the interaction coming from these two nodes as well. And the question was, is this here reducible into that, or is it different in general? Now, the equation that we had, that we started to look at, was really inspired by something called the Growth model, which is also like a model called the decentralized consensus model. And it's a very simple model that finds its roots in, I think it started in the 1970s or 80s for graphs. And what it tells you is the following. So a certain node tries to go to the value of its neighbors, basically. You try to go to the average of the value of your neighbors. But here, because we decided to incorporate multi-body interactions, what we would have is the following. So node I, if it has a certain interaction with node J and K here, well, it will try to go to the value of these two nodes. So we try to go to the average of those values. But what we have is that there is an influence function that means that the two nodes here are going to be more influential on you if their values are very similar. So if this function s here should be maximum when j minus xk is small, when the two nodes are very similar, and it's going to be small when the two nodes are different, which basically means that the two nodes j and k are very different. And so here it means that if two nodes are similar, this node will be very much convinced. I will try to get to those values. Whereas if these two nodes are very different, they will not be able to reinforce their message, and this node will not be very much influenced by their values. So you try to go to the values of people agreeing with each other, basically, through these higher order interactions. Now, if you look at this model, why did we look at this model? Actually, we looked at it because, so first of all, it's possible to, well, at any point in time, it's possible to define a certain weighted adjacency matrix, but that's not really important here. What is more important is to show that actually in the case when the S is a constant, so if you take S to be a constant, this model becomes linear, right? You can just get rid of this. What you have, it's possible to show that when you do your sums, what you will actually have is a linear model. And what can be shown is that, so if the dynamics is a linear one, you can rewrite this equation here that involves the tensor in terms of an equation that involves a matrix. And that matrix can be thought to be as an adjacency matrix of a projection of the hypergraph. So actually, if you take this to be a constant, this equation reduces to an equation to a consensus model on a graph, on a weighted graph. And actually, in this weighted graph, what you have is that the weight of an edge is going to be simply the number of hyperedges to which this node, this edge belongs to. And so it means that once you have a linear model, actually the dynamics on the graph or on the hypergraph are exactly equivalent to each other. Which also means that if you want to have a difference between the graph and the hypergraph representation, you need to have that the x is non-constant and you need to have a nonlinear dynamical model. And honestly, initially when we saw that, I just found it super cool. And then when you thought for a second, you say, oh, yes, of course. Well, why of course? Because if you have a linear model, we know that a linear model on a finite number of states can be represented by a matrix. And if you have a matrix, you can see that matrix as an adjacency matrix. And so it means that necessarily, if you have a linear model, it can be encoded by a matrix, and that matrix can represent basically a weighted graph. So necessarily, if you have a linear model on a hypergraph, it can be seen as a linear model on a weighted graph, which just need to be careful about how you do a projection. But if you do your projection well, then what you will have the dynamics on the graph and on the hypergraph are just the same, basically. Now, what about when S is not constant? When S is not constant, then you can get differences. And these differences can lead to some interesting phenomena. So for instance, here I just have like a tiny example. We wanted to show like how the presence of triangles will lead to new phenomena that couldn't be observed with graphs. And what we did was to consider two cliques, two big cliques, and then we would have the triangles are connecting the cliques, but the triangles tend to have one edge inside A and two edges from A to B. And so in a way, what you have is because of that, you have an asymmetry in the way the triangles are connecting the A and the B's, right? And what it basically means is that if you start with like black values here and white values there, well, in the case of the nonlinear dynamics that I explained, because these two nodes are very similar, they will have a big impact on this one, whereas these two are very different and they will have a small impact on that one here. Which basically means that due to this asymmetry and due to the nonlinearity of the dynamics, the black values will have a higher tendency to invade the white than the white would have to invade the black. And indeed, here, if you look at this row here is the initial density of, I forgot, no, what is I forgot what it is actually. Um, well, essentially, what you observe, so P is the fraction of triangles that are directed in one way or the other. What you observe is that depending on this P, on whether or not the triangles are pointing from the left to the right or from the right to the left, we can observe that we have some sort of like a S shape, which means that if you have triangles that point a lot in one direction, well, and here that would be from the left to the right, asymptotically, all of the nodes will become black. Whereas if they point in the other direction, you will have that all of the nodes will become white. So there is due to the nonlinearity and to the higher order interaction, you do have the possibility for flow to invade it in a certain direction inside the hypergraph. Now, so first message, when you look at dynamics on hypergraphs, if you want to get really something new, you need to go to nonlinear dynamics. Otherwise, you just need to do a projection. Yet, it's not the end of the story because so when you have a hypergraph, in principle, there are many ways to do a projection. And there are multiple ways to define projections and to define random walks on a hypergraph. And here in this work with Timoteo Carletti and Duccio Fanelli, what we just did was to explore a family of random walks where that would lead to different projections and trying to understand, let's assume that I have a hypergraph, I choose different types of random walks. Each of them can be associated to a different projection and that will be associated to different weighted graphs. what would be the outcome of algorithms on those hypergraphs, on these projections. And what we could observe is the fact that, so here, like you have like a very simple example where in this case you have like a click of size 3, a click of size 3, and 3 clicks of size 2. And what you can observe is that depending on the kind of projection that you use, you can observe very different types of communities or clusters when doing community detection. So for instance, with one family of model, you start from, so for certain parameters, you have 6 nodes, and then you directly go to the 2 groups of 3. Whereas for other projections associated to other ways to do the projection, you would also start from 6 nodes, but then you would go and find the 3 groups of 2, basically. And so it basically means that depending on the way you implement your random walk process, you have different projections, and these different projections may lead to different outcome. And in this case, it would be leading to different communities, different community structures. Cool. So that was about the first part of my talk. So the second part is about something that is different. So very often as I said, according to me, what makes networks so wonderful is the possibility to have indirect interactions. And indirect interactions are encoded by the notions of walks and paths. Now, the thing is that if you observe an interconnected system, there can be situations where you can actually measure what are the walks or what are the paths that are followed by some entities. And there can be situations when actually, I'm sorry, I'm just trying to move because otherwise I cannot see. So there can be situations where the path that you observe would be very different from the path that would be associated to the graph that you built. So here is an example where let's assume I take some series data and I observe the sequences. I can see that I can go from A, C, D, and then here I do B, C, D. And this is what I observe from the data. So if I represent those paths with a graph, I will observe that I've transitioned from A to C, from B to C, from C to D, from C to E. And now if from this representation that has lost the exact sequence that were in the data, and I start to do a random walk on this, well, what I would observe is transitions like those where I go A, C, D or A, C, E equally, B, C, D or B, C, E equally, right? So you lose the information of where you come from when you decide where you go to the next step. Whereas in the data, what you observe was something that was very, very different. And what you observe here is the fact that so if you use some non-Markovian information, you can have a very different representation of the path than the one that would be associated to a graph that is Markovian by essence. Now, so essentially, one way to look at it is the following. So I started by saying that in old times, people would be looking at collective dynamics in the mean field where everyone would be interacting with each other, right? Then people started to look at constraints, and those constraints would be the fact that not all pairs of nodes are possible, and those would be you would have a network representation. Well, here what we have is that not all of the walks are equally likely to happen within that network, and only a subset of them, or maybe some of them are more frequently taken than others. They're not taken uniformly, as you would expect them to be in a network representation. So again, you are constraining your model potentially informed by sufficient data. So here are just like two illustrations about it. And so in this case, we looked at the way papers would be citing each other. And so what you have is, let's assume that I have a paper from this journal. It's been cited by a paper in Nature. And you ask the question where, and so a certain paper here is cited by a paper in Nature. And you ask what is going to be the journal citing this paper that I have here. And that can be seen as some sort of like a flow of information from paper to paper. Now, if you coarse grain the papers by journals, well, and if you just look at the way, sorry, I'm lost in my windows. And if you just look at the way the flows would be represented in a Markovian or a non-Markovian representation, you can observe extremely different flows, basically. And these very different flows are associated to the fact that, well, if you have a paper in plant physiology cited in Nature, it's cited again in plant physiology. and not in a journal of applied mathematics, for instance. And actually, these type of flows can be observed like across domains. They can be observed in these journals, also in the way the people are traveling, for instance, taking planes. So if I go from New York to Chicago, where do I go next? Well, in a first order representation, I can go equally anywhere. If you look at the data, there are some specific choices that are taken by the travelers, basically. And and actually, if you start to compare more quantitatively the properties of walks as you observe them in a network representation or in the data, they can be very, very different. So for instance, looking at the two-step return, the property that you go from I to J and then go back to I, well, it's going to be typically much, much higher in the higher order representations than it is in the first order one. So clearly, the properties of the walks are very different in the data than they are in the network representations. And well, in this work, we basically what we tried to do was to enrich networks and to develop tools that would be using flows of walkers that would be more closely related to the empirical trajectories. And if you do that, for instance, and if you do community detection, what you can obtain, and I don't have too much time to talk about it, are very different clusterings and very different types of clusters that are the one that come from a first order representation than the ones that are coming from a second order representation. Now, something that is annoying when you go from first order to a higher order representation is the fact that you are actually the state space that you have explodes. So if you go from the first order to the second order Markov representation, typically that is something that increases drastically the size of the space that you need to use to describe your data. And because of that, well, first of all, it's very computationally expensive, but also it's very likely that you will not even have enough data in order to calibrate your model. And ways to do it are to find ways to have some concise representations that are somehow interpolating between first order and second order Markov modeling order. And one way to do so is quite recent, is this one here that we did with my student Rohit, where we we propose a way to interpolate between first and second order like Markov representations using some ideas that come from non-negative matrix factorization. Now, I think I just have 2 minutes left, so I'm going to be super fast. So what about non-negative edges? So there are many situations where well, classically, when you think about weighted networks, you think about weight as frequencies, and frequencies are positive, right? And similarly, if you open a book on graph theory and you look at algorithms for weighted graphs, they will tell you to start with that the weight should be positive because that's the most natural way to do it. And also certain concepts, such as the notion of shortest path, are ill-defined in the case of graphs with negative entries. Yet there are many situations where you can have negative entries in graphs. And here's an example of a dataset we collected where we'd have negative entries to encode a disagreement between people in some online debates. And so clearly there are situations where negative edges happen and you have a collection or a combination of positive and negative edges in the graph. Now, actually, if you try to look how to generalize notions of graphs with positive entries to graph with positive and negative entries, well, a very important notion is the notion of structural balance. And structural balance basically tells you the following. So it tells you that if you have a graph, there is a certain type of structure that is balanced. And for a graph to be balanced, you need to have that along all of the cycles of your graph, you will have that the number of negative edges is even. And here's an example. This graph is balanced. And indeed, if I start from here, I do a cycle, I take one negative edge, a second negative edge, then I come back. I take two negative edges, so my graph is balanced. All of the cycles will have an even number of negative edges. Now, what is wonderful about those graphs that are balanced is the fact that it's possible to show that if a graph is balanced according to the definition I just gave, it means that it can be partitioned into two sets of nodes, here these ones and those ones, such that all of the positive connections are between the nodes, well, between nodes of the same type, and all of the negative connections are between the groups of nodes. So it basically means that if your graph is balanced, you can think of two factions. Inside the factions, the people agree with each other. Between the factions, they disagree with each other, basically. And the thing is that in this kind of structure here, this type of balanced structure has very important impacts on some spectral operators, some linear operators. So here, I don't think that I have much time, so I'll just say that in words. So in the case of classical graphs, when you want to investigate the connectivity of a graph, you would be using a Laplacian. And the Laplacian is very important because its eigenvalues, well, something that's important is the fact that the multiplicity of the zero eigenvalue tells you about the number of connected components in the graph. Well, actually, in the case of signed graphs, what you have is something called a signed Laplacian. And that signed Laplacian also have a very nice interpretation in terms of consensus dynamics. But what is interesting is that in that case, the value of the smallest eigenvalue tells you whether or not the graph is balanced or not. So it means that in the case of graphs, the value of your second smallest eigenvalue tells you if the graph is connected or not. Here, it tells you if the graph is balanced or not. So I like to think of a balanced structure as the equivalent of disconnected components in the case of signed graphs, basically. And because of this parallel that exists between the theory of Laplacians for unsigned and signed graphs, a lot of the algorithms that are existing for the Laplacian can be generalized to the case of the signed Laplacian. And for instance, there exist like clustering methods, there exist like embedding techniques that are using this signed Laplacian in order to find information in graphs that are not exactly balanced, but are almost balanced, basically. And I think that unfortunately I will have to stop now. Just for those of you interested, actually, if you look at the notion of balance, you can actually also generalize it to the case where on the edges, you have not only positive and negative values, but you can also have complex numbers or even matrices. And in that case, what I like about it is it reminds me of my old days as a student in physics doing some quantum mechanics where you would have the possibility for some interference to propagate inside the graph. Because every time you have a rotation, for instance, and because the complex number can be seen as leading to rotations, you would have that certain signals can propagate in one way along a certain walk, another way along another walk, and there is a possibility for these signals to reinforce each other or to interfere with each other. And depending on these patterns of interference, it can lead to extremely different asymptotic properties for some dynamical processes. Okay, so I'm sorry that I had to be a bit fast for the end. So here I think it's time for me to conclude. So well, I assume that most of you are interested in like multi-body interactions, right? So, but nonetheless, I wanted to open up a little bit the scope and to emphasize that, well, first of all, it should be recognized that networks are wonderful, right? Networks are wonderful, are a wonderful language. They are the language of connectivity. They are the language that tells you how to deal with connections. But there are situations where there might not be enough. And there are situations where you need to enrich it and to adapt some of the ideas that you know from graphs in a more general settings. One possible way to do it is to go to higher, like multi-body interactions, such as with hypergraphs and simulation complexes. Others is to deal with mathematics based on paths, more than mathematics based on edges. Also, there is the notion of balance that is quite important if you are opening up to the case when the edges are not simply positive numbers, but are more complex entities. And well, I think that definitely there is a lot of fun ahead of us and ahead of you, I suppose. Also, in looking at the relation that exists between all of these higher order representations. And yeah, I think that I covered everything that I wanted to tell you, and I thank you very much for attending this talk. Thanks.
Thank you very much, Renaud. Thank you for this amazing talk. And if there is any questions from the audience, please you can unmute yourself and ask.
I had a quick question.
Yeah.
It was from all the way in the beginning, I think figure 13.2, like one of the first slides on the random walk.
Here.
Yeah, this one.
Yeah.
Because I think I understood that you can use the like the time scale to kind of understand or to separate groups of nodes.
Mhm.
For example, the red and the blue group here. But I was wondering how this works for multiple nodes. If you want to separate three or four or multiple nodes, is that also possible? Because I can imagine
Yeah.
that the probability structure will become very complicated.
Yeah. The thing is that in this case, so I just use, well, first of all, I use the Karate Club because it's a slide that dates from the time when the Karate Club trophy was still existing. So it was important for me to have the Karate Club as part of my slides. But the thing is that so indeed, like so actually, if you go on this small book here, oh, and I forgot on the last slide. So and I will send the slides. There is a link. Where is it? A link to a book where some of these ideas are developed. So I will send it to you so that you can have access to it if you want. But the thing is that indeed, like so in if you have a graph that is made of more than two communities, well, basically what would happen is that, where am I? I'm lost here. Okay. So if I have, let's say, three communities, well, the way to think about it, the way that I like to think about it is to think of communities as imperfect connected components. And so indeed, like, and the kind of prototype that you look for when you look for communities are a situation where you try to abstract your network that is a bit noisy by something where you would just have three or four or five connected components, basically. And here in this case, there would be two connected components. And the thing is that if let's assume that you have a graph made of four connected components, then what would happen is that what's happening in each of the connected component is completely independent of the others, right? And in that case, you have like a perfect timescale separation. It takes infinite times for information to propagate from one cluster to another, basically. And in that case, you would have that if I start from cluster A, I will reach the stationary state inside A, cluster B inside B, C, and so on, right? Now, let's assume now that, and in that case, what will happen if you look at your transition matrix of your random walk, you will actually, so the transition matrix will have the dominant, or the stationary state is associated to the eigenvalue 1. And you would have that there is a multiplicity of 4 for that eigenvalue because there are 4 independent solutions. E- each solution of, well, each of the communities is independent of the others, basically. So you have like, now, if you add just a little bit of noise to this structure and you start to add a few random connections between the clusters, then actually you can use like perturbation analysis to show that, well, if you think about your eigenvalues, initially you had 4 values at one and then the others, right? And what will happen now is that I will have one value that remains at one and three that becomes very close to one but slightly below, and then the others are very far apart. And so it means that if you look at where your eigenvalues are, if your graph is almost made of four clusters, well, what you will have are 4 values that are very close to one and the others that are far apart. And basically, what would happen then is that for for the time scales that are associated to eigenvalues between the 4 first ones and the fifth one, and there is a big gap between those. Actually, around those times, all of the fast modes have relaxed. So it means that locally everything happens, and the information has not had enough time yet to go between the clusters, basically. And actually, this kind of like example that I gave here, that is not taken from like, well, it's an empirical one, right? But if you do the experiment with some stochastic block models, where you can impose certain density of connections between and inside inside the clusters, you can actually explore better the distribution of those eigenvalues, identify when you have a spectral gap, and this spectral gap leads to this timescale separation. And usually, well, that if you observe a certain timescale separation between 6 nodes and the rest, then that would be indicative of the presence of 6 clusters, for instance, in the data that you have. Well, this is in the ideal case, right? Usually in practice, it's going to be much more messy than that. But if you do experiments on graphs that are sufficiently dense inside the communities and sufficiently sparse between the communities, it's really easy to at least to have like an intuitive idea on how diffusion would be taking place in such a system. I hope
Okay,
it
yeah,
answers your question.
yeah, thanks so much.
Thank you, Cyril. Cyril, yes.
Okay, any other question? I'll take a look also to the chat. Well, I do have a question by
Yep.
myself. So, regarding pairwise networks, we have an intuition of what a community is, and
Mhm.
we can relate it to the Laplacian, to diffusion models, and so on. But when we come to other models or hypergraphs or whatever, it is not intuitive to define a community and not even a Laplacian. So I was wondering whether there is a correct or a well-defined way to deal with communities and in parallel with a higher order Laplacian.
Well, the thing, usually my intuition is that as soon as you generalize the model, you have choices to make, right? So that was even already the case for graphs. When you have a classical graph and you start to put weights, or if you can start to put directions, notions of, for instance, of communities or any kind of notion you can be interested in is going to be more model dependent. You're going to be having more parameters to deal with and more modeling choices to make in order to define what you look for. And so, for instance, in the case of communities uh, for hypergraphs, for instance, well, here I mentioned this work. This is an old one that is somehow related to communities because it was interested in the notion of cut, and the notion of cut is one very simple and powerful concept related to the notion of communities. It tells you well that there is like a bottleneck in terms of connectivity between certain subsets of nodes. And in that case, the kind of approach that they had was to have a way to measure the cuts by the density of hyper edges, essentially, or motifs, because that would be in between the two sets. Well, like the other way to do it that would be related to that would be to have, and there has been approaches like that based on stochastic block models or also based on modularity, for instance, where you would be counting the density of motifs inside the clusters, right? And you would say that a good community is such that most of the triangles are inside the clusters and that there are few triangles between the clusters, for instance. And actually, there was already a version of modularity for cliques, I think already 15 years ago by Arenas, I think, that was proposed a long, long time ago. That they didn't really talk about hypergraphs by then. They were looking at cliques, but there was this type of intuition that you look for clusters in terms of the density of certain patterns. In that case, that would have been cliques that can be thought of as hyperedges these days. Now, and so it means that there are certain approaches that are based on counting motifs inside or across the clusters. Another way is to use these kind of random walks types of ideas. And here, well, in this work that I mentioned in passing, it was there. Yeah, so in this work that I was mentioning, so what we did was simply to say, well, if you do random walk and a linear random walk, and the linear random walk is going to be equivalent as a random walk on a weighted graph, depending on how you define your random walk process, you can then use the map equation, or you can use Markov stability, or you can even define modularity on these weighted graphs. And the kind of communities that you will have are going to be very different depending on the kind on how you define your random walk process. And the thing is that in that case, it was using this. I think that the main motivation for this work here was not necessarily community detection, but to show that you need to be careful when you project. So when you do projections, well, we know that we lose information, but actually we may actually have extremely different conclusions depend from the same data, depending on the way the projection has been made. Now, something that potentially would be interesting to do is to generalize these ideas, and maybe that people did that because there's been so much work on hypergraphs over the last 2 years that I lost track, to be honest. But so I guess that someone must have, and maybe it's you, and I apologize if you were the one who did it. There would be ways to define, random walks on the hypergraph itself. Now that I think about it, well, people have done things that are related using at something called looking at something called the Hodge Laplacian. So the Hodge Laplacian is a way to define diffusive processes not on the nodes, but on the hyperedges, essentially, or on the simplices. And in that case, you then have a possibility to encode random walk processes that are, or diffusive processes that are not defined just on the nodes, but are defined on on the edges or on the triangles and so on and so forth. And there have been works that go in that direction, but there are many, many more parameters that need to be dealt with in that case. So the things already for networks, people very often ask me, what is the best community detection method? And already there, I never have a very satisfying answer. So I'm afraid that in the case of hypergraphs, it's even more complicated.
Okay, thank you very much. Any other question? Okay, there is a question in the chat. So, and of a person who cannot unmute. Okay, so I may read it for everyone. So I have heard of the metrics valued edges in the networks before, but I'm not familiar with them. You talked there about model choices, and this is maybe one of them, but what kind of information do the matrices typically encode that higher order interaction don't? Um, some other kind of multiple interaction types, spatial dynamics, or something else?
So can you just like rephrase the first sentence? Because I didn't understand the first sentence.
The very
Sorry.
first was I have heard of metrics valued edges.
Yes.
Okay.
Okay.
If you want, this question is in the chat. If you want to
Oh,
have it.
okay. Yeah. So the things that so maybe they're referring. So the thing. So maybe I will give an answer. I don't know if it's the right answer. So the things that. So for instance, so so there exists there. So one type of generalization that I've not talked about today is something called multiplex networks. So in the case of multiplex networks, what you can think of is situations where you have, let's say, n nodes, and then these n nodes exist across different layers, and you have different types of connections inside the layers, basically. Now, the thing is that when you have such a multi-layer network representation, such as a multiplex representation, it's possible to encode, let's say that I have, I don't know, like T layers and n nodes. You can encode everything by something called a supra-adjacency matrix. That is a big matrix of size n times t times n times t. So it's a much, much bigger matrix. And and the thing is that indeed, like so, and then already at the time, people would say, well, why would you need a multiplex network? Because what you have essentially is just a network on a bigger space. That's true, but at the same time, sometimes having a certain data representation in mind changes, first of all, the constraints that you have when you develop algorithms, but also change the way you think about it. And it's very different to think of a big graph of size nt than thinking about all of these t copies of the n nodes that are basically that are interacting through different types of channels of communication. It leads to different intuitions and different algorithms as well. Now, about the situation where on each edge, let's assume that you have like n nodes, and then on each of the nodes you define a vector of size, I don't know, k, and on each of the edges, what you have is a linear transformation that acts on the vectors that are defined on the nodes. So, and that would be this thing that would be called that would be a graph where on each of the edges, what you would have is a linear transformation now. Well, again, this system can be exactly equivalently be represented again by a supra-adjacency matrix, where you would have, again, k times n times k times n entries that would encode how the element I on node J is affecting elements alpha on node beta or something like that. So it means that you would have interactions between the elements of the vectors that are defined on each of the nodes. And so it means that again, the question would be, why would you care about having a network with complex weights? Because it can be encoded exactly by a bigger matrix. But the thing is that for the very same reason, once you adopt a certain data representation, it completely changes the way you look at the problem. And for instance, also with my student U here, UTN, well, after this work on complex network with complex weights, we considered the situation we would be having matrices on edges. And we arrived at what I think to be interesting generalizations of the notion of structural balance that only made sense because we had been looking at it from that perspective. So it means that this notion of coherence, as we called it, that can be seen as a generalization of structural balance, is meaningful and naturally arises if you look at the problem from the notion of complex of matrices on the edges. And it's correct, but it wouldn't make much sense if you were to look at it in terms of a bigger matrix. And sometimes, well, finding the right way to encode your data is critical if you want to infer to infer some important properties that are inside it. I don't know if I gave the answer to the question, but I hope that somehow I answered one question at least.
Yes, I think that James is satisfied with the answer.
Okay, thanks. Thank you, James.
Thank you. So, any other question? Very quick ones, maybe. Let me see the chat. Apparently no. So, thank you very much again, Renaud, for this great talk. Hope to see you soon in Marseille, baby. And
Yeah.
thank you everyone for attending. I may stop the recording.